Well, welcome back for the fifth in our series of short video tutorials in this mini library I've created for the chemical equilibria topic. So far we've actually met at least 5 different equilibrium constants. We've met Kc, Ksp, the solubility product, Kw, Ka and Kb. And in this video tutorial we're just going to take that one step further, and we're going to talk about something called the Henderson-Hasselbalch Equation, which is a pretty important equation for acid and base chemistry. Through a lot of different contexts. You'll see this popping up throughout chemistry, biology, different sorts of physical systems, and so on. It's an important one to have a bit of a handle on. There's a few tricks nature can play to what we say buffer systems against sharp changes in pH. And if you can get a handle on this equation, it would certainly help to understanding this idea of buffering solutions. Well, this is a pretty rudimentary introduction, but it's a good place to start. Consider the equations below. I've got a chemical reaction on the left and the Ka equilibrium constant expression on the right hand side, and we met these two in the previous video tutorial, and we saw how we could use that Ka expression to determine the pH of a solution. Now, what if we were to add some acid to a solution which already had a large concentration for the conjugate base? Remember, we call this guy here the conjugate base. And I urge you to sort of think, how might this be similar to the common ion effect, which is something that we talked about with sparingly soluble inorganic salts. So a different topic, a different kind of equilibrium, but how might this scenario be similar to that scenario that we discussed when we talked about the common ion effect? Your understanding of the Le Chatelier principle should tell you that if the concentration of A- is already high, you should not be able to observe as much of the acid HA to dissociate. Okay, so what we're saying here is we have buffered the solution with a pre-existing amount of the conjugate base. The good news is there is an equation which allows us to measure this, and it's called the Henderson-Hasselbalch equation, and it looks like this. The pH equals the pKa, which is not something we've talked about yet, plus, oh look, there's a typo on this slide, the log of A- over the concentration of A- over HA. So what's this pKa? Ka values for most acids, as I've mentioned before, are pretty well known. You can quite readily find a table of well-known Ka values. They're also often expressed in pKa form. Now you can convert Ka to pKa in exactly the same way you can convert H plus or H3O plus to pH. In other words, the pKa equals the negative log base 10 of the Ka value. Let's investigate this using our old friend acetic acid as an example. Now here's an example question, and I'm just going to fix up my equation, which seemed to have dropped an important part there, a little log. For example, if we have 50 mils of 0.2 molar acetic acid and we have 50 mils of 0.2 molar sodium acetate, and we mix them together, what is the pH of the solution? Okay, there's a couple of things I'll mention first. The first thing is, what's sodium acetate? Sodium acetate is this guy here, and it's a salt. And you might like to think of this as being the anion, and of course sodium is going to be the cation. But it's a molecule when it's solid, in some sense, I suppose, an ionic molecule. Chuck it in water and it really readily dissociates, and you get these two ions here. Okay, it's a very soluble salt, so you can assume that if you try and dissolve this stuff in water, it's going to completely dissociate. Now, hopefully at this stage you guys are looking at that and thinking, that looks pretty familiar. That is the conjugate base for acetic acid. That's the first thing I'll say. The second is there's just a small trick with this question, so don't forget about what we're doing here, because it's going to affect our concentrations. That's a beaker, by the way. I'm not a very good artist, but it's got 50 mils of acetic acid. Whoops. I've got another beaker, and it's got 50 mils of our sodium acetate. I'm going to mix them together into another beaker. What is the final volume? It's 100 mils, isn't it? So I put it to you that the concentration that we see in the question, which for both of these things is 0.2, once we've mixed them together, you actually have to adjust that concentration. We have the same amount of sodium acetate, for example, but now it's in twice as much of the solvent. In other words, its concentration will have halved. We'll come back to that. And I'm just going to erase this here so I can actually do the calculation. Okay, here we go. So we've got 50 mils of 0.2 molar acetic acid, 50 mils of 0.2 molar sodium acetate mixed together. What is the pH of the final solution? Well, the good news, it's really just a case of substituting it all into this equation here. So the pH equals the pKa. Now let's just put this straight in. It's the pKa, so it's going to be negative log, base 10 of the Ka value, which we've been given in the question, which is 1.8 times 10 to the minus 5. And that's going to be plus the log of the concentration of A minus. Now, A minus is this stuff here. Now, at this stage, you might be thinking, yeah, okay, but what about this stuff here? When you chuck this stuff in water, doesn't some of that dissociate? Isn't that going to increase the amount of A minus? You can't just take it from this guy here. The good news is this is a weak acid. So even though a very small amount of the acetic acid is going to dissolve in water, it is, as we saw in the previous video tutorial, only a very, very small amount. In fact, it's about 1,000th of this stuff will actually dissociate. So 99.9% of it will stay as the molecule. So we can assume that the concentration of A minus is 0.1 molar. It's not 0.2 because remember, we've actually diluted our concentrations here, and it's half of what it should be. And numbers are the same, so we should see the concentration of the acetic acid stay at 0.1 as well. We sub all of that into our calculator, and we should see this gives us something like 4.74. And of course, this is the log of 1. The log of 1 is 0. So the pH of this solution is 4.74. Now, hopefully you watched the previous video tutorial where we determined the pH of acetic acid when it was by itself in water. And we saw that the pH of 0.1 molar acetic acid was about 2.9. In this case here, when we throw in that buffer, you can see that the same concentration of acetic acid is only giving us a pH of 4.7. It's nowhere near as acidic, or we should say the amount of H3O plus in solution is significantly less. And so the effect of adding a buffer, it buffers us against stronger pHs, if you like, in the case of an acid. Okay, that's a nice simple example. I'm sure you can find a few more complicated ones if you want to practice your technique. And that's it for now for video tutorial number 5. In the next video tutorial, we'll talk about gas phase scenarios.